So welcome to the third session of the Polish NLP Meetup. This is super exciting. This session is actually gonna be in English because we have a guest from Berlin, from deepset.ai, Branden Chan, machine learning engineer working in deepset. And Branden will talk to us about neural search and scaling this up to multiple documents in production. I'm super excited about this topic because it's a practical, industry application, and I'm also very excited about deepset. So when I trained Polish bird a couple of months ago, I reached out to deepset because you guys trained German birds before that, and you gave me a lot of nice tips and advice. So I appreciated that, and I appreciate the spirit of sharing and education that you do in the community. So Branden will I guess this is the dedicated session for this topic. And after that, we're gonna do a quick survey among our community members so that we want to understand better where you come from, what are your needs, what are the next topics that you would like to listen to in this meetup. So with this, let me hand over to Branden. Branden, thanks again for joining our meetup.
Sure. So let me start sharing my screen. And let me know if you can see my slides here on the screen.
Yeah, it's working.
Okay, great. Well then, yeah, let's get started. Yeah, thanks very much, Derek, for having me here today. It's really nice to be able to talk to you all about a topic that we at deepset are really focused on right now. It's neural search. So the idea is that we want to scale question answering to multiple documents. And I'll kind of motivate this throughout my speech and give a sense of how we can bring together this research with industry applications. So let's just try to get to the next slide. Yeah. As Derek mentioned, yeah, I work for deepset. I'm a machine learning engineer there. And we are situated in this position somewhere between what's happening in academia and what is needed in industry. What we see from the research side is that there's a big surge in deep learning-based NLP happening right now. We see a lot of transfer learning happening. We see a lot of developments in terms of more powerful language models. And we also see a lot of focus on this task known as question answering. This has really driven us to want to build something that actually works for people. And so our focus has been on our open source framework, Haystack, which is here to help you build industrial neural search. It gives you all the components, all the state-of-the-art pieces in order to create something that will actually work for your documents and give you the best kind of search that is possible right now. The technology that we use is heavily driven by this QA, this deep learning, transfer learning-based question answering. And it's open source, so as a developer, you have absolutely everything you need to build an end-to-end system. And if you happen to work in an enterprise setting, we also have features on top of that, which are optional, which will help you with building this scaled, stable production system. And in our history as deepset, we've actually worked with a lot of industry partners, people like Siemens, Airbus, Sparkasse, and Datev. And through projects with them, we've really gotten a sense of what is really needed to get a system running in a big corporation. So what I want to show first off is what is this neural search that I'm talking about? Why do we want to scale question answering, and what can it do for us? So I'm going to quickly switch over to a demo that we have. Oh, skipping ahead already. So this is a very basic demo that we've got. And in here, we have a store of documents in the back end, and they're all about the company NVIDIA. And we might have this huge amount of documents and want to answer a question like, how did revenue develop in 2019? We don't really know how to find this document. Control F gives us far too many examples, and it's not really organized very well. This is where neural search can kick in. So with this neural search application here, we can simply ask this very question. We have a model that is reading this question, trying to make sense of this question, and then reading through the documents in the store. And you can see that it is now returning certain documents and specific parts of documents which can answer this particular question. So here we have revenue for the fiscal year 2019 increased 21%. For fiscal 2019, revenue was 11.72 billion. You can see, yeah, we have a couple of different documents which are pretty relevant to what we're interested in. We might also ask something like, how is the outlook? So here we have, the model highlighting these sentences which say something like, we expect cryptocurrency-related revenue to be negligible going forward, or that we expect competition to increase from both existing competitors and new market entrants. So we can see that we're really getting a kind of a granular search. This is the sort of search power that we expect from a web search engine like Google, and Google definitely is doing some incredible things on that front. But we want to be able to bring this to your own store of documents within your company to have basically Google for your own documents. And so with that in mind, I want to talk through the different NLP components and engineering components which help us build up this kind of a system. So I'm going to split this talk up into a couple of different parts. I want to talk about language models, which I expect that most of you are probably kind of familiar with, so it'll just be a little bit of a refresher. I'll talk about the task of question answering, especially about this very popular task called Squad. And then I want to talk about scaling this to open domain QA so that you can actually do this on a large store of documents, making that efficient, making that actually work. So I just want to do a quick refresher on language models. What does a language model do? Well, language models, practically speaking, are able to convert text input into a set of vectors, which accurately kind of capture the meaning of these words. One side effect of being able to do this well means that it learns a sort of a distribution of words. And a good language model should actually be able to guess what is like missing words in a sentence. So if we have the sentence, the fox something's across the street, a good language model is actually able to suggest words that would fit into that gap, like runs, trots, or walks. How do we do this? So standardly, large transformer-based language models now are trained using large unlabeled text corpora. You feed in a large amount of text, it reads through it, and it gets a sense of how this language is working. Standardly as well, with pre-training tasks, you would do something like masked language modeling, as well as next sentence prediction. This is at least the kind of norm that was set up by BERT. And there are lots of variations on this, but masked language modeling still remains the most popular task that there is right there, and quite an effective one as well. Once you have a trained language model, you will want to start doing some downstream tasks, do something a little bit more practical with this language model. And in doing so, you would want to exchange these prediction heads, which are tailored to the pre-training tasks. You'd want to initialize a new one in there, and you'd want to fine-tune it for your specific task, like NER, or question answering, or document classification. Just some examples of some popular language models. Derek mentioned a little bit earlier, BERT, which is probably the one that really set off this boom in language modeling and showed just how effective this methodology is. There's Roberta and XLNet, which are in some ways variants of BERT. And there's also MiniLM that I want to bring up, which is a very recent one. But there's also a very big push right now to build models that are actually smaller, but more efficient and more performant, that can still match up to BERT, but run much quicker on your devices or on your systems. I'll actually talk a little bit more in detail about MiniLM a little bit later on, so you can hold on for that. But I just want to stress that, there are a lot of language models out there. BERT is one of these really big seminal language models that has spawned a lot of models that are variants of it or improvements upon it, like SpanBERT, which improves on the way that the masking is done. There's Roberta, which is a more robust style of training of BERT without any drastic architectural change. There's Albert, which is also a sort of a more robust and more performant version. And there's these set of smaller models like QBERT, DistilBERT, and MiniLM. And that's just a few of them. There are a lot of them. This is a graph kind of just showing sort of like a family tree of them. Those of you who are keeping up with news might be interested in the top right corner in GPT-3, which there's been a lot of buzz around lately. But yeah, it's very interesting seeing what's happening in this field. And if any of you want to talk to me about any of these models later on, I'd be more than happy to discuss with you and share what I know about them. But I just want to show the workflow that I described earlier. So how does a language model actually help us do the task of question answering? So as I mentioned, to train a language model, you would pass in a large unlabeled text corpus. After reading through that, this language model would become trained. You can move on from there and initialize what we call a prediction head on top. Could be, as I said, could be NER, could be question answering, could be document classification. And you pass in your task-specific data set, let's say question answering. And through this, the language model outputs these word vectors that we've been talking about. And these word vectors serve as the input to the prediction head, which then gets trained on this task. Ultimately, you can move on from that data set, and now you have a trained system which will be performing question answering for you. So let's move on and talk a bit about question answering. What does this task look like? So you might start off with a question like, what is Berlin? And then have a text passage, a single text passage here. In this case, we have a Wikipedia paragraph about the city of Berlin. And in asking this question, a good model should be able to highlight the span of text which best answers this question. So a good model should be able to say, Berlin, the largest city of Germany. This isn't a straightforward task for quite a few reasons. So for one, there is an interaction between text and questions. Sometimes you might have the one passage, but you might have different questions, and the model has to kind of respond differently to each one of these. There are a large set of potential predictions because any point in this passage could be the start or end of an answer span. And a good model really needs to have a good contextual understanding of a potentially very, very long text. Sometimes you need to remember what came at the beginning of the passage to highlight the actual answer, which maybe comes towards the end. One popular approach to this is to train what we call a reader model or a question answering model to identify the start and end of the answer span. We can, as I showed before, fine-tune a language model on labeled question and answer pairs through that workflow that we saw in the diagram earlier. And Squad has become somewhat of a default data set for this. Squad is the Stanford question answering data set. And it works on, it's built off of Wikipedia paragraphs, and it's what we see on the left there is quite a close representation of what goes on in Squad. So at this point, I just want to trace through what is actually happening when we perform question answering. What goes into your language model, let's say here in this case, a BERT model, is that you pass in both the question and the passage together in as text. BERT generates these word vectors, and these word vectors are passed on to the prediction head, which then performs the prediction and tells us the start of your answer is token 7, the end is token 11. That will hopefully be the largest city of Germany in the case that we just saw. But in a more granular look at this, I want to sort of describe what is going on with the prediction head there. Because the prediction head gets all of these vectors and generates two numbers, the start logit and the end logit. This prediction head will actually iterate over every position, over every one of these word vectors, takes it as input, and generates this pair of numbers until you've done that for every position. And then at this point, the model has to pick out the start and end logits with the highest values, which give you the most probable answer. as you can see here. What I want to stress here as well is that Squad is a very, very popular, very effective data set, but there have been a lot of data sets which have actually improved upon Squad in various ways. So starting on the left, there are a lot of data sets now which introduce very different data structures, some which integrate images like visual QA, some which have tables like Wikitable or Wikitable questions. There are multi-hop data sets which require some sort of fusion of information from different parts, or sort of or require synthesizing information from different parts and taking separate steps in order to get towards an answer. There are a lot of question answering data sets now in different languages. So we see there F-Quad, which is a French squad, K-Quad, which is Korean squad, and Spare-Quad, which is a Russian squad. There are also some multilingual data sets, which are a combination of a few languages, like Tidy. It's a combination of 11 different languages, but specifically chosen to be very typologically diverse languages to really challenge these systems. On the right, there are data sets which have scaled up in various ways to present more open domain-like tasks. So we've got OpenQA, MS Marco, TREC, and web questions. And there are also data sets which introduce very different answer type formats. So natural questions in the top right there introduces yes/no answers. It's able to, you can ask it something like, is Berlin in Germany? And it can respond, well, there are annotations which will say yes or no, and a model has to be able to say yes or no, not necessarily by extracting something from your passage. So why are we so interested in question answering now? Why are there so many people who are suddenly paying it so much attention? Well, when transformer models came into popularity, we saw that the performance of question answering significantly shot up. We can see a graph on the right of the performance on Squad, the state-of-the-art performance on Squad. And this boost that you see towards the end of 2018 is actually mostly due to BERT. BERT really set the new benchmark for what was possible with question answering. And it really has made it possible to use these sorts of systems in a much more practical setting now. So yeah, there's a really big momentum in research, as we saw just by the amount of data sets in that previous slide. As I mentioned, there's a lot of new language models coming out, as well as lots of new data sets, which include more of reasoning and synthesis, for example. There's also a lot of interest in making these models and these systems much quicker. There, as I mentioned already, there are a lot of distilled models. There's look into the task of pruning models and different attention mechanisms. And also, there are a lot of people trying to make systems which are robust across different languages, that are multilingual, and that can even zero-shot to new languages. And on top of this, we see that there's a lot of demand from industry for systems that can answer questions when applied to large document stores. There's really a growing information workers who really need to perform these sorts of queries and don't really have the exact tooling for it just yet. And there's this growing gap between the power of web search and enterprise search. And actually, I've been talking a lot about search here, but this technology that we're talking about is actually quite flexible. We've seen a lot of cases where, for example, a company has an incoming stream of documents and want to keep asking the same questions over each as a form of either classification or as a form of summary. And there are also a lot of people who are interested in building chatbots and having this sort of question answering ability as a fallback when they're not able to identify a specific intent. So yeah, there is definitely a lot of need to make these systems practical, make them flexible, make them scalable. And this is what I want to talk about here in what we're calling open domain question answering. So what is open domain question answering? It is very similar to question answering, except the question answering that we saw before, except that we're now trying to look for an answer within a large collection of documents. So once again, we might be asking this question, what is Berlin? But we might not just have one Wikipedia article, but a large store of them. And we expect the system to still be able to give us the answer, the largest city of Germany. And with this, there are its own set of challenges. So for example, reader models, these question answering models that I've been talking about, have a limited input length. And once you start adding longer documents and more documents, you're gonna have to find ways to engineer around this. Speed is definitely an important consideration when building these systems. To make these really practical, we really need to be able to complete as many queries as are coming in. And especially with these new transformer models, which are very powerful, we can get very good results, but it is still a challenge trying to get them to run at a speed which is practical. There's also the challenge of the aggregation of predictions. So different documents may have very valid candidate answers, but there needs to be a certain amount of logic and processing to decide which answers to return and how to rank one over the other. One very popular approach to this, and one that forms the core of Haystack, the framework that we've been working on, is something known as the retriever reader pipeline. And it looks something like this. So starting on the left, you might have a store of all your documents, and this is passed on to a component known as the retriever. The retriever is a lightweight filter, which tells you which documents might be relevant for this query that's coming in. And its job is to take all these documents and return just a subset of these to the reader module, which are these transformer-based question answering models, which actually do the close reading, have some understanding of how these sentences are put together, and choose the span which best answers the question. So to give a sense of what can be achieved by adding in this retriever step, if we ran some experiments with about 7,500 documents from the natural questions development set, we used a Roberta base model and a Tesla V100. And when we performed a query using just a reader, it took about over 3 hours to perform that query. But with a retriever, with having this quicker filter, we can actually reduce this down to something in the range of 0.5 to 2 seconds per query and still maintain pretty good performance. And so I want to talk a little bit more about these specific components, because there's a lot of work and a lot of different options with each of these parts. I'm going to start with the retriever here. So there are quite a lot of different papers looking at ways to retrieve information from large stores of documents. And as a baseline, the first step that we're going to look at, the first approach that we're going to look at are sparse baselines, something that's something like BM25, which is a variant of TF-IDF, and it's something that is implemented in Elasticsearch. There's a slightly more performant version known as latent retrieval via ICT. This uses a dual encoder architecture and relies on this inverse close task on raw text. More recently, there has been the Realm approach from the team at Google, I believe, who treat this as a task of language model pre-training, but they augment it by retrieving some documents first. And actually, I want to focus in on this last one, which is dense passage retrieval, which I'm going to talk about in more detail. This is also a dual encoder approach to retrieval, but the way that they train this is quite clever. They use question passage pairs with in-batch negatives. So I want to show you what this looks like in this next slide here. So the idea behind this is that we have two separate language models, two separate BERT encoders. One which deals with a question that is coming in. This BERT model will take in this question and give a vector representation of that. And then you might pass in all the passages in your document store to a second BERT model. in order to create these vectors, which then get indexed in your database. And when you perform a query, you're doing a dot product between the vector that represents the question and the vector that represents the passage. And this is the scoring function to see how relevant this document is to your question. The real power of this is the real advance in the way that they do this is really how they perform the training. So when they perform training, they batch in a very interesting way, whereby they pair a question with a positive passage, a relevant passage, and then a set of negative passages. And the way that this is done is that basically a lot of the passages within the batch are they're each paired with each question is paired with one positive passage, but the other passages in that batch, which are paired with another question, count as a negative to this first question. And this forms a very efficient way of training this dual encoder architecture and really getting the most out of your data set. And what they find also is that by combining multiple data sets in their training, they're actually able to get much nicer performance, much more powerful performance. Practically speaking, on the inference side, what you would want to do, as I said, is to pre-compute embeddings for all of your documents, and you would want to index it to some sort of database that is optimized for this sort of similarity search, such as Facebook's face method. And then each time you perform a query, you would want to retrieve your k-nearest neighbors. So that was on the retriever side. On the reader side, I want to talk about how the latest models perform on Squad as a benchmark here. So here I have a set of different models that were taken from the Transformers Model Hub. And these are models that have been also fine-tuned on Squad. And this shows their performance on the Squad task. And we start off with BERT Base on the left, Roberta, which is a little bit better, and Electra as well, which is actually a very interesting new architecture, which actually gets rid of this masked language modeling technique, and it's much more sample efficient. What I really want to point out here is this mini LM here, which is also a distilled model, like DistillBERT at the end, but it is about a third the size of BERT Base, but actually outperforms BERT. And we see this as a very, very promising direction, and it's something that I think is worth really diving into, because they have some very interesting approaches here. So what they start off with in this distillation method, what happens is that you start with a bigger trained question answering model. Or sorry, no, not even a question answering model in this case. You start with a bigger trained language model, and you initialize a smaller one, and you get this smaller one to try to mimic the behavior of the larger teacher model. And in this paper in particular, they use two different types of transfer. They have something known as, you can see this on the diagram on the right. They have attention transfer, where they get the student network to try to mimic the matrix of query key scaled dot products. This is something that is very crucial to the attention mechanism. And also they get it to mimic also the value scaled dot product matrix as well. This is a lot of detail and quite a deep dive, but what I really want to stress here is that, yeah, their performance is actually just really, really quite striking. So for a model that is a third the size of BERT Base, it actually outperforms it on the GLUE benchmark. On Squad, it actually outperforms BERT by 4.9 absolute F1. And in terms of inference speed, it's a little bit variable depending on how you are performing your inference, but we've seen speed ups in the range of 1.3 times to 2.7 times the speed of BERT Base. So we see this, yeah, this is already very, very usable, but we also see this as part of a trend of a set of research that is creating more powerful models that run faster, that have a smaller memory footprint as well. So this has got us really, really excited. And at this point, I want to switch over to Haystack, which is how we've been playing around with these open domain search systems. And I want to show you what it's like to work with this repository. So a lot of the components that I've just been talking about, you can see represented in the code here. We start off with a line here to initialize a document store, such as an Elasticsearch document store here. In the next red square, we see this retriever, which is simply initialized by calling, in this case, dense passage retriever in that line there. We would have a reader next. In this case, we have support for both FARM, our own transfer learning framework, or Hugging Face's transformers. And then you combine the retriever and reader components into a finder, and finally call this finder in order to form a prediction. So yeah, as mentioned, it is open source, and you can already start working with it. You can already use it to build end-to-end open domain search systems. It's modular. It's made to be very easy to extend. It's made so that you can really tweak these individual components yourself. We have a variety of different components for you to choose from, different options that would work better in different settings. And we also have a REST API and Docker for deployment. I want to just mention a couple more of these options here. So for example, yeah, in the document store, as I mentioned, we have Elasticsearch, we have SQL, perhaps you want to work with in-memory documents, or we also have Face, which will be coming in the next couple of days. On the retriever side, you might have some, you might want to work with some sparse forms of retrieval like TF-IDF or BM25. But we also have dense passage retrieval already. We're actually really excited about it when it came out, and yeah, couldn't wait to get it in there. Would really encourage you to try it out because this is really, it's been really quite impressive what it can do. And yeah, as with the readers, we've trained a set of BERT models fine-tuned on Squad. We've trained Roberta and also Mini LM fine-tuned on Squad. And I really want to mention here actually that we have an integration with the Transformers Model Hub as well. So whatever question answering model there is out there that you want to start working with and to plug in to your open domain search system, you can do that simply just by naming the model when you initialize the reader. And as I said, on top of this as well, we have the Docker images, we have an API, we also have a labeling tool if you really want to get your model to be adjusted to your own domain. So yeah, I really encourage you guys to try it out. We've been having a lot of fun developing it and working with it, and we really think that there's going to be more and more of a need for it, and we really want to hear what you guys are going to build with it so that we can yeah, just get a sense of what's really possible with these models. So to wrap up what I've been talking about, yeah, just want to recap that language models, this is really the core of what's really been powering modern NLP. And they really form the core of most modern NLP systems now. QA systems have also recently become a lot more powerful thanks to these language models, but also thanks to new data sets and just a lot more new attention on improvements here. And if you want to scale a QA system to an open domain setting, you end up building something that actually provides a very powerful solution to enterprise level information needs. And yeah, if you want to start playing with this yourself, I'd really encourage you to try it out with Haystack already, which is there to create an end-to-end open domain QA system. And to really finish off, I want to just kind of talk about what might be coming in the near future. We really see that there will be new data sets which focus even more on new data formats, more on tables, more on figures, more on images. That's really how we see this field developing. There are going to be a lot more new retriever approaches. There's definitely a lot of interest from research teams out there right now. There's a lot of look into generative QA. So models which don't just extract a span from your existing documents, but they read your existing documents and then formulate a sentence which answers your question. And we think that there was also going to be a lot more work on this idea of reasoning and synthesis, how to really put together pieces of information from different parts of a document or even from different documents, how to kind of weigh them up. So yeah, thank you very much for listening. Here we have just some links for you here. We have the link to our GitHub for Haystack. You can follow Deepset and myself on Twitter and on LinkedIn. And I also want to mention that we're hiring right now. So if you're a senior ML engineer or a front-end developer, back-end developer, or a DevOps solution architect, please get in touch with us. And thank you very much.
Thanks a lot, Branden. I have a couple of questions myself, but I want to open up to the community first. I saw there was one question posted in the chat.
Let me have a read of that. Yeah, so I'm just reading this question from Bartek about the K number, talking about how many documents should the retriever pass on to the reader. And as it is in Farm right now, sorry, in Haystack right now, this is something you can set. This is something that you can set to 1 or to all or to some reasonable number in between. Practically speaking, you're going to want to set this based on a certain trade-off. So as I said, reader models, very powerful at reading through documents and extracting a good answer, but very computationally expensive. They're going to take a very long time. So if you reduce this K number down to something relatively low, you are going to speed up your system, but potentially sacrifice a bit of performance if, say, the actually most relevant document wasn't within your top K. Yeah. Reading the next question. Okay, sure. So from Al, I believe, what are the necessary steps to customize Haystack, say for a specific domain and specific language? Okay, sure. So in practice, actually, we found that these QA models are actually much more robust than we expected. Like in the past, you really want to adjust your models to your domain language. Say you're doing automotive or legal or something like that. I just want to start off by saying actually that these QA systems, which are these QA models that are trained on things like Wikipedia, there's sort of enough just general language understanding to really be able to cover, and we've seen it be able to cover things like patents and legal documents. But if you still really want to give it that extra level of fine tuning, what you would want to do is focus first on the reader. So the reader is this QA model. You would want to create new question answering labels for your specific domain. If you're really serious about it, you might also want to train all the way from the language model. Maybe you want to train like a science BERT, which some people have done, or you might want to create a legal BERT and then perform this fine tuning on top. This level of fine tuning, this level of adding, like creating these new labels is actually why we created the labeling tool. It is a QA labeling tool. So yeah, you can have your own documents, you can write your own questions, and you can highlight the spans which answer that so that your model starts to get an understanding of how legal language or like technical legal questions work, something along those lines. And as for the specific language part, yeah, a lot of language models out there right now are single language models, but well, the BERT base that we talk about is actually in English, but there are, as Derek mentioned, he's trained a Polish BERT, there's a German BERT, there are a lot of different BERTs out there. I want to actually mention one specific model, which is XLM Roberta, which is a huge scaled version of a Roberta model that actually addresses something like 100 languages at once. And we did some evaluation on that, and it's actually surprisingly powerful. So if you don't find a single language model for the language that you're working with, I would actually encourage you to give that a shot and see how it is. Yeah. I'm moving on to the question from Anwesh. I'm just going to have a read of it now. So Anwesh asks, have you considered using Universal Sentence Encoder from Google for the retriever? I have to be honest, I'm actually not familiar with the Universal Sentence Encoder. I'd be curious to hear about it if you want to get in on the chat and yeah, explain to me maybe what it does. If you have a mic, actually, you could maybe even unmute yourself and
Hey Ben, can you hear me?
Hi, yeah, I can.
Hey, thank you for the session. I think it's very useful. So the universal sentence encoder is kind of a model which helps you to do sentence similarity.
Mhm.
So you can take a passage or a sentence and you can compare both of them and use a cosine similarity to see how far or how near they are.
Okay. Cool. Yeah, no. That sounds like something very similar to dense passage retrieval. But
Yes.
maybe one thing I'll mention about dense passage retrieval is that one of the really important things about it is that there are two encoders. So how do I put this? Like, we've seen systems in the past which have like a single encoder. So you can turn a sentence, you can project a sentence into a latent space. But when you're doing a if you're doing the kind of search where you're like asking a question and looking for an answer, the encoding for a question might actually look very different to the encoding for a document, because questions are generally going to be much, much shorter than the document, and they have their own sort of style. What you really want to do is project both of these into a shared space, but kind of recognize that one is coming from a question and one is coming from a document. So I don't actually know exactly how universal sentence encoders are used, but I would just want to stress this point that there's a difference between performing finding relevant search documents and finding just, say, documents or sentences that are similar to each other.
Got it. Thank you so much.
Sure. I'm reading the question from Shari Singh now. Just give me a moment here. Okay, sure, yeah. So Shari Singh asks, how do you rank the reader outputs? Like, which exact answer will be shown to the user first? Or is it the retriever passage ranking that is being considered to rank the exact answers also? So in terms of the ranking, the retriever actually doesn't play a role in this so much. It's more on the side of the reader. And if you remember from the slide talking about the logits, how this prediction head produces numbers for each position to show how confident it is that a token is the start or the end of a span, these are the values on which we build a final score for a span. So practically speaking, in our implementation, we add the start logit and end logit to give a final score, and then we basically just rank these spans based on that score. There's one complication that was introduced. There's one complication that is relevant because of Squad 2.0. Squad 2.0 introduces the no answer. So maybe you ask a question that just can't be answered by your database. And in that case, there's actually a very different sort of logic that goes into trying to figure out how relevant is no answer relative to the other ones. I probably won't go into too much detail into that right now, but I would just say that that's a different kind of logic altogether, and it really requires something known as aggregation. But I can point you to some blogs and some resources which address that, and I'll post those in the chat after this. Yeah. Going on to the next question, how about multi-word words? How are they processed? Could I actually get some clarification on what you mean by multi-word words? Do you mean words that are kind of joined together by hyphens? Or do you mean words that are just very long compounds like you get in German? I wonder if do you have a microphone right now? Would it be possible to talk to you? Yes, I can hear you.
Yeah, so Grześ, you might need to unmute yourself about this multi-words. Yeah. I guess this might be a question about tokenization. I don't know, potentially.
Mm-hmm. Mm-hmm. So can you give me an example of a multi-word word? Maybe I'll move on to the next question and come back to this one when we have an example, so I can better answer it. But yeah, I guess at this point I'll move on to your question, Derek. What's your experience with handling longer text? Does chunking work better, or new architectures like Longformer? Sure. So yeah, the approach that we're taking is actually the chunking method. So if you have a very long document, you set a maximum passage length, and then you cut this document up into these chunks with some overlap as well. And yeah, we've seen a lot of these architectures which promise much bigger, much longer attention, much more efficient attention mechanisms, which allow for much longer documents. We actually haven't seen this very efficiently applied to QA yet. And we're very excited about it. We really do see this coming in the future. But just at this moment, we found that the performance with chunking is actually still very strong. And yeah, for now, it's working quite well. And there are a lot of other areas that you can improve to kind of make up for sequence length issues as well. So we've got an eye on it, but really chunking's quite good right now. Yeah. I'm going to move on to the question from Darius. What is the accuracy improvement comparing dual encoders on QA pairs to typical BM25 approach? Is it significantly better, or can it be worse in some cases when dealing with long passages or specific language and vocabulary? Yeah, I'm sorry, I don't have the numbers at hand, but this dual encoder, this dense passage retrieval method that we saw is what we're adopting now. It's really actually the most powerful. The performance is just better than BM25. But one thing I do want to stress is that actually there are certain cases where one will perform better than the other. So for example, BM25 is really just looking at lexical overlap. So in cases where you maybe have a name, BM25 doesn't have a semantic representation for this name, but just by seeing that it occurs in another document, it already kind of can tell that this is probably something relevant. That's something that it can deal with, this sort of out of vocabulary items. This is something that these dense methods are actually a little bit weaker at. So if you give it a name that it's never seen before, it actually doesn't build a very good representation for it, and therefore doesn't do this similarity comparison very well. And so actually in the near future with Haystack, we see that going forward, we want to do sort of a hybrid approach. So why don't we perform both BM25 and this dense passage retrieval and actually score by some combination of these two? That's kind of where we see the future. Yeah. Moving on to Derek's next question. Can QA solution be hosted on a CPU server? Yeah, this is a question we get a lot, and it can. It just depends on how much time you have per query. Practically speaking, we've not really gotten into a point yet where we feel like we can really recommend building a system that is purely CPU reliant. The most promising directions here are these distilled models. As we said, with mini-LM, we have a model that is a third the size of BERT, but actually performs even better than it on question answering. Still, yeah, transformers are computationally expensive, and we think it's going to be some time yet until we actually get to really production systems which are purely CPU based. We're inching towards it, yeah. What metrics did you use to evaluate Haystack? From Adam. So we actually split it up into two steps. We kind of evaluate based on we evaluate the retriever and the readers somewhat separately. And so starting on the reader side, it's basically mimicking what like the squad task is. It's talking about exact match, which is did it get the exact answer span that we want, and also F1, which is kind of how much did those answers overlap, even if they're not perfectly aligned, how much did they overlap? And yeah, there's actually an evaluation set of evaluation scripts within Haystack, which you can already play around with so that you can actually test out some different models as you like. On the retriever side, yeah, you start off with a big store of documents. We get the retriever to return a certain number. I don't remember that off the top of my head. It might be something like 20 or so. And then we try to find out how many of those that are retrieved are actually directly relevant documents for the initial query. I'm moving back to this multi-word expressions issue, and I'm just going to quickly look at this document. Okay. Yeah, look, I think ultimately this is a tokenization issue. As these modern methods work, they use something like a byte pair encoding. So you have a vocabulary. So I guess what I'd say is, like, imagine you have a vocabulary that is just characters to start. It's all the characters of, let's say, the alphabet. And using this, you can actually already tokenize anything that occurs in the English alphabet. But you might want to do something better, whereby you realize the word "the" comes up a lot. And so you now add that to your vocabulary, and then you realize, I don't know, the numbers come up a lot, so you add that to your vocabulary. You basically join your characters so that they form bigger words. And by doing this, you form a vocabulary that can cover absolutely any kind of input, so long as it's in your character set. And so if you have some sort of a multi-word expression or a multi-word word, if the tokenizer has never seen this before, what is likely going to happen is that it's going to break it up into chunks of words that it does sort of understand. And this is quite cool, actually, because I think it then allows it to sort of play a little bit of morphology. Maybe it's never seen the word, I don't know, forgetfulness before, but it can split it up into forgetful and ness, and then sort of make some sense of it through these separate parts. I hope that helps. And then I'm going to answer this next question by Christoph. So he says, I guess Transformers does not have problems with MWE, like United States of America. Yeah, sorry. So I guess this is still relevant to this multi-word expression issue. Yeah, I would expect that a transformer model with a good tokenizer would split that up into United States of America. They're generally actually, the vocabulary is actually generally don't contain white spaces within them. So they're going to, the largest units seem to be words. So I think it would split it into United States of America. How it would make sense of this as an expression is more in the model weights. The model weights see these components, and they kind of, it's in the model weights that it realizes, oh, these 4 tokens are occurring in sequential order. I actually need to compute sort of a new representation for them, which actually covers the fact that these 4 together mean a specific country. So yeah, it's really a combination of these 2 things that finally build you something sort of representing morphology and how we compose meaning out of smaller units. Yeah.
I think this was the last question in the chat. Let me check with folks if there's anyone that wants to ask a question on the call. Okay. If no more questions, then Branden, this was an awesome session. I learned a lot. I thought I already understood some of these topics, but actually I learned a lot. I'm excited, especially about finding up this mini LM. I somehow missed that. It seems very promising, and hopefully within our reach with less of a hardware specs. So that's exciting, and overall I think we're definitely gonna try out Haystack, and thanks a lot for everything that you're doing for the community in terms of both the software contribution and the open source, and also the education and the sessions. We really appreciate it. Thank you very much.
Yeah, no worries. Thanks very much for having me. And yeah, I'm going to share some of these links, I think, just in this chat here, and I'll also I have some slides if you would like. I can
If
pass
you
on the slides.
if you can share the slides, we have a public repo for the meetup, so
Okay.
I would post them here. That would be
Great.
awesome.
Let's do that.
Okay.
Then maybe I'll give you all the slides and the links together in one.
And I will publish that in the summary of the meetup.
Great. Awesome.
Appreciate it. Thanks a lot. For the folks that are still on the line, and Branden, this will be probably for the meetup members. I want to do a quick survey. This will not take a lot of time. Feel free to stay with us if you'd like, but I understand you may want to drop. That's probably less relevant for you.
I will stay on, and I'll just prepare some of these links.
Awesome. So let me present, and folks, this will take just a couple of minutes, but this will help. This will help us, better prepare these meetups in the future. So let me share my screen. If you can go to, and I hope you can see it. If you can go to www.menti.com and use this code 824412, then I have just 2 questions, and this is like free form. So the first question is really about you. Like, tell us about your role, why you're interested in NLP, anything that you'd like to share with the community about yourself. The second question will be more about the meetup and what you want to get out of it. But the first question is really trying to understand you and the broader community, the people that we have in this group. So let's hope that this will refresh live as you kind of post your answers. I hope we should be able to see everything on the screen. I will not summarize it. I think we just want to learn about this community. Okay, we have the first answers. Awesome. Thanks everyone for sharing. This is very insightful. I have a lot of folks that I think we can tap into in terms of the future presenters. I see a lot of experience here in this write-ups. I'll give it 1 more minute and then we'll switch to the next section, question, and the last question, which is about the future meetups. Okay, last 10 seconds to hit enter if you've written up something that you still like to share on this slide. Okay, so let's move on. So this question, and this is the last question for today. Tell us what you'd like to this meetup to be. Like, what's the format? What are the topics? Presenters? Maybe you would like to present something yourself. Anything else you'd like us to consider for the future meetups? And you can also write this in Polish if you prefer. The session was in English because we had international guests, but I think for this, for the purpose of this survey, Polish is fine as well. Thanks for sharing the topic ideas. This all look very interesting. Okay, counting to 10. So hit enter before we close out. These are great insights. Okay, awesome. Thank you, everyone. This like taking notes of I'm taking notes of the feedback. Really appreciate it, and we'll come back to you soon on the next meetup. We have a new co-organizer that volunteered to join in the organizing team of this meetup, and I hope we'll introduce you in the next session formally. So, but for now, thanks everyone for joining, and looking forward to reconnect you in a couple of weeks probably. Thanks everyone.